And with that, I ask you to join me in welcoming the CNPC team.
Hello, I am Max Shen from UC Berkeley. I'm a professor with joint appointment in the Department of Industrial Engineering and Operation Research, and also with the Department of Civil and Environmental Engineering. I'm also an honorary professor at Tsinghua University. I want to first thank you for coming here to support our presentation. I also want to congratulate all the finalists in this prestigious competition. I want to take this opportunity to share with you our project with CNPC, which is short for China National Petroleum Corporation. Our project is natural gas supply chain optimization, where we try to jointly optimize the production, import, transmission, storage, and sales decisions in the supply chain. Before I give you more details about the research problem, I would like first to invite Mr. Xu, who is the Vice President and CFO of the Planning and Engineering Institute of CNPC, to give a brief introduction of the company. Mr. Xu.
Okay, thanks, Professor Shen. I'm Xu Yinjun from China National Petroleum Corporation. First of all, as the Vice President and CFO of CNPC's Planning and Engineering Institute, I'm very pleased to introduce my company briefly. Since 2000, with the rapid economic development, the gas industry in China has increased very fast. The average annual growth rate was over 14% in the last 17 years. And the natural gas's proportion in the first energy consumption was about from 2 in 2000 to 7 in 2017. So, as the largest oil and gas company, CNPC produced and supplied roughly 70% natural gas domestically in 2017. The next video will give you some more about CNPC.
CNPC, China National Petroleum Corporation, is China's largest oil and natural gas producer and supplier, and is an integrated energy corporation with business covering natural gas production, import, transportation, storage, and sales. In 2014 to 2017, CNPC ranked the top 4 in Fortune Global 500. CNPC operates over 50,000 kilometers of natural gas pipelines, which is the second largest natural gas pipeline network owned by a single corporation around the world. CNPC has built 4 major natural gas fields in Sichuan, Tarim, Changqing, and Qinghai, with an annual production capacity of more than 100 billion cubic meters. CNPC imports pipeline and liquefied natural gas from foreign countries. Each year, CNPC delivers over 150 billion cubic meters of natural gas to over 5,000 end users all over the country. The underground natural gas storage owned by CNPC can store over 10 billion cubic meters of natural gas.
Okay, Professor, please.
As we can see from the video, CNPC plans to play a major role in promoting natural gas in China. However, as of 2014, it was unclear whether China's pipeline network had sufficient amount of capacity to meet the increase in demand. It's not easy to answer this question, mainly because of two reasons. First, there are thousands of nodes in the network. The network is interconnected and forms many cycles. Second, the physical laws governing the relationship between flow and pressure in the pipeline is highly nonlinear and non-convex. To help CNPC to make better decisions about their pipeline network design and supply chain optimization, we plan to answer the following two questions. One, how much natural gas can be transported by a given network? And two, what is the optimal transmission plan based on the location of the supply and demand and the different purchasing and sales price in the network? We plan to address these questions by integrating flow dynamics equations into an optimization framework. Many of us are familiar with operational research. Some of us might even be expert on network flows. At the beginning of the project, I thought this natural gas supply chain optimization problem might just look like some of the network flow problems we learned from supply chain textbooks. The following video actually will demonstrate that the natural gas network flow problem is actually much more complicated than the textbook model we learned. I take this as a comforting explanation why the petroleum engineers get paid much more than many of us industrial engineers.
In a road network, the control is the number of vehicles per unit time. But in the natural gas pipeline transmission, the control is the gas pressure. If the gas pressures at nodes A, B, C are all 8 megapascal, natural gas stays static. If node C's pressure decreases to 6, natural gas starts to flow. If node B's pressure increases to 10, gas flows from B to A and C. When we change gas pressure, the flow directions and the gas flow rate change simultaneously and non-linearly. Different from vehicle traffic, natural gas cannot just flow by themselves. We need to control gas pressure and temperature to control the gas direction and flow rate. The relationship among gas flow rate, pressure, and temperature is non-linear and also non-convex. Assume that we need to transport 10,000 cubic meters of natural gas from Xinjiang to Beijing in 1 month. We set the natural gas pressure at Xinjiang at 8 megapascal. As natural gas flows to Shanxi and Beijing, its pressure decreases to 7.5 megapascal and 5 megapascal respectively. What if the pressure at Beijing cannot be lower than 6 megapascal? The first solution is to increase the natural gas pressure at Xinjiang so that the pressure at Beijing is above 6 megapascal. The second approach is to build a compressor at Shanxi to increase its pressure.
As we can see from this video, the natural gas network flow problem is indeed harder than our textbook problems. So at the beginning of the project, we were really curious to know how these higher paid petroleum engineers solve this problem. Next, Mr. Xu will give us an introduction of the method they have been using before our project.
Okay, before this project, we used the manual method and Excel to solve this problem. The next video will show us how we did it.
The first step is to divide the whole system into more than a dozen subsystems. The second step is to establish the internal balance of production, transmission, storage, and sales amounts within each subsystem by using Excel. The third step is to adjust the decision made in the second step based on management team's experience and feedback. The fourth step is to seek a preliminary balance among the production, transmission, storage, and sales amounts in the whole system by adjusting the interflows between each subsystem. The fifth step is to check whether the amount of natural gas in each subsystem is balanced according to the preliminary balance of the whole system. If not, we go back to the second step and iterate.
Okay, the disadvantage of this manual method was that it might take too many iterations, both in the whole system and subsystems. It also relied on too much the engineer's working experience. So, different people often obtained different results. Most importantly, it did not guarantee the maximization of profits. Furthermore, the manual method did not give us different or more scenarios. So, the next video will show us the disadvantages in details.
We encountered a major management problem in 2012 when planning the natural gas usage for year 2013 to 2020. We divided the whole transmission system into 15 transmission subsystems and assigned the associated flow balancing tasks to 8 engineers. Each engineer was responsible for the flowing balancing of his or her assigned subsystems. Later on, these 8 engineers discussed the interflows between subsystems to ensure the flow balancing of the whole system. However, they found out new inconsistency in their own subsystems. The process did not converge in weeks.
So, in 2012, we decided to work with UC Berkeley and Tsinghua University to apply operations research to improve our natural gas supply chain planning and optimization. Next, Professor Sun will introduce the methodology we use.
It became apparent that the manual method will not work anymore for CNPC. Instead, our team came up with a supply chain optimization model where we try to maximize the profit by integrating production, import, storage, and sales decisions in the whole supply chain. If you look at the diagram, the key difference between this gas supply chain versus our textbook supply chain lies in the yellow part, where we explicitly model the pressure and the temperature and how they influence the flow in the network. We want to make sure the model will satisfy these two constraints. In the network flow constraints, we want to make sure the gas flow is balanced at every node. Supply and demand falls in the right ranges, and gas flow, pressure, and temperature are controlled within the safety ranges. And in the pipeline constraints, we make sure that the pipeline's flow rate and pressure satisfy the following dynamic equations. The pipeline constraints that you can read from the PowerPoint is very complex. We just give you a simple example with only 2 nodes. Node 1 have a pressure of P1 and temperature of T1, and node 2's pressure is P2 and temperature is T2. And the gas flow from node 1 to node 2 can be expressed as a function of P1, P2, T1, and T2. It is clear that this constraint is nonlinear and non-convex. On top of this nonlinear and non-convex constraint, there are several other factors that make the CNPC natural gas supply chain problems even harder to solve. The next video will show you all these complexities.
The elevation difference between Xinjiang and Beijing is over 2,000 meters, which has non-negligible effects on gas transmission. The demand in winter in China can be twice as much as the demand in summer. Price of gas imported from different countries vary much. Pipelines of CNPC form a large-scale complex network, which increases the complexity of the whole problem.
After considering all these complexities, we end up with a large-scale, nonlinear and non-convex mixed integer programming problem. This model has about 37,000 constraints and 15,000 variables. No existing commercial software can solve this problem. Instead, we came up with two approximation methods to solve this complex problem. The first approach is a piecewise linear approximation, and the second approach is a three-stage convex relaxation method. In approach one, we approximate the nonlinear problem by a mixed integer linear programming problem. This approach is quite successful in solving small-sized problems, but is not effective in solving large-scale problems. The computation time always exceeds the maximum limit. And simplex sometimes might return different optimal solutions if we are using different computers. In approach two, we use a three-stage convex relaxation approach. We first solve the convex relaxed problem. If the solution from this relaxation is not feasible, we then solve an energy minimization problem to get a feasible solution. And in the last stage, we solve for pressure and temperature given the flow rate from the second stage. These two approaches have their own pros and cons. Approach one has higher solution accuracy, but requires a longer time to calculate. Approach two has higher computational efficiency, but is less accurate than approach one. To validate our model and solution method, we have to answer the following two questions. First, can our model reflect the real pipeline characteristics? The answer is yes, because our fluid dynamic models are based on industrial standard and verified by field experts. And we further validate our results by comparing them with those from the specialized pipeline simulation software. The second question is, can our approaches, our methods guarantee feasible solutions? For the linear approximation method, we use up to 20 segments to guarantee solution accuracy. For the convex relaxation problem, we first prove theoretically that we can find optimal solutions if the network structure is simple, such as a tree network. For CNPC's network, which has 1,285 nodes, we did extensive simulation, and our result shows that the average gap of our method is smaller than 0.3%, and the maximal gap is no more than 7.5%. We also realize that the real problem is stochastic in nature. To deal with uncertainties in price, supply, and demand, we analyzed many scenarios and did extensive what-if analysis. So after all these tests, we are really satisfied with our approach. So we want to convince CNPC to use our method and our models, but it was really challenging. So we spent a lot of time trying to learn the user's needs and requirements, and also compare our results with the known results from their previous research. As operation researchers, we actually get involved not only on the modeling side, but also on the software development and testing. We have written about 230,000 line of code on the algorithms, and also on the data processing and the user interactions. We also had many training sessions with CNPC employees to let them know about operations research. Eventually, CNPC decided to use our software in 2014. Next, I would like to invite Mr. Xu to share with us their experience using our software.
Okay, based on the methodology introduced by Professor Sun, the project team developed a software to make plans on natural gas pipeline transmission in networks with any topology. The software can provide reliable plans in transmission system with 5,000 natural gas sources, 10,000 nodes, and 20,000 clients efficiently. Next, I will show you the basic functions of the software.
The decision support system has 5 components: data input, data check, unit conversation, optimization, and data output. Data are first imported from the database into the optimization system and stored in the memory. Second, the arbitrary numerical data are converted into data with standard units. Third, the system checks the data for correctness. Then, the natural gas pipeline planning problem is optimized by the algorithm users chose at the very beginning. After the calculation is finished, the results are converted and output. During software development, we worked to provide more choices for users and make the software interface more user-friendly. First, the main interface displays the pipeline network loaded from the database. In the software, the geographical information of each node is stored in the database. The design is similar to that of commercial map software. The user can move, enlarge, and shrink the network similar to using a Google map. A user can also click on each node and arc to check its information. Second, when the software is initialized, a user can select the objective functions and other system settings. For example, the objective function can be either linear or piecewise linear, and the physical parameters can be computed in various ways. Third, the team designed 9 levels of data checking, including magnitude, conflicts, size relationship, overlaps, network topology, and checking module required by other software like TGNet. Software is designed to give the error prompt and let users to choose whether continuing the calculation. Fourth, the users often do not want to wait too long without receiving any information. So the system is designed to help users learn the schedule of calculation.
Okay, the successful implementation of our software significantly increased my company's profit. In the past 3 years, CNPC has obtained $530 million profit increment. This huge number included 3 components. The first component, $340 million, was from the reallocation of gas selling amounts. According to the optimal plans from the software, we increased the selling amounts in the higher price areas and decreased the selling amounts in other areas. Therefore, we got more revenue. The second component, $188 million, was from the reduction of purchase and transportation costs. For example, in 2016, we increased the amounts from the liquefied natural gas terminals, which was cheaper relatively, and decreased the amounts from the import pipelines, which was more expensive. The third component, $2 million was from the labor cost saving. At the same time, based on the optimal results from the software, we postponed the constructions of 4 main pipelines for 5 years on average, such as the middle part of third west to east pipeline. This decision saved roughly $20 billion of current capital expenditure budget. The successful implementation also significantly increased the working efficiency. For instance, it took 3 days to finish an annual plan by manual method. After the implementation of the software, it takes only 40 minutes. Moreover, this efficiency increment allows us consider more scenarios. In July 2017, one regulator valve in the second west to east pipeline broke down. CNPC's operations team ran the software and obtained a new transmission plan quickly and met the demand of the downstream users in a timely fashion. The project has brought not only huge economic benefits for my company, but also significant social benefits. For example, with the rapid increase of natural gas usage in Beijing, the air pollution content decreased by 35.5% from 2012 to 2017. Mr. Xie Zhenhua, the special envoy of Chinese president for climate change affairs, gave high praise and placed high hopes on this project.
管网运输优，清华大学和美国加州大学伯克利分校的天然气管网运输优化团队进入国际知名的弗兰兹厄德曼奖的决赛。中国政府始终坚持创新、协调、绿色、开放、共享的发展理念，将节约资源和保护环境作为基本的国策，努力成为全球生态明建设的重要参与者、贡献者和引领者。目前，我们在能源领域努力推进能源生产和消费革命，构建清洁低碳、安全高效的现代能源体系。天然气作为一种优质、高效、清洁的低碳能源，加快天然气产业的发展，是中国能源升级和结构优化的需要。预计到2030年，天然气的消费量将达到6000亿方，将占一次能源消费的比重15%左右，逐步会发展成为中国的主体能源之一，发展前景十分广阔。该团队以运筹学理论为基础，开展天然气运输网络的优化研究，不仅为企业带来了巨大而持续的经济效益，也为国家能源优化、民生改善、节能减排、环境保护带来显著的社会和环境效益。我相信该团队运筹学研究在天然气领域应用的前景广阔，对提高天然气 在中国能源消费当中的地位起到更为积极的作用。谢谢。
After realizing the power of operation research, CNPC has decided to establish a lab on natural gas supply chain optimization. One of the key missions of this lab is to apply operation research to every aspect of their natural gas supply chain, ranging from the upstream wellheads to the downstream end users. Meanwhile, operation research at CNPC is being broadly considered as an improvement process of making things better. With this broader view of operation research, we plan to develop systems that will integrate market forecasting, economic evaluation, artificial intelligence in order to form a data-driven supply chain optimization platform for natural gas. I also want to mention that our approach of handling pipeline dynamics can be modified and applied to the fuel minimization problem and the transient natural gas pipeline scheduling problem. Furthermore, we believe that the innovative method in this project can be applied to many of the continuous process industries, such as the metal smelting, chemical engineering, oil refinery, and wastewater treatment. Let me conclude the presentation with a quick summary. With a collaboration between UC Berkeley, Tsinghua, and CNPC, our integrated decision support systems helped CNPC improve working efficiency, save $20 billion in their planning budget for the next 5 years, and directly increase profit by $530 million. This project not only helped promote operation research at CNPC, it also helped us come up with new and interesting research problems. Our project also has a big environmental benefit in China by giving CNPC more confidence to supply natural gas, which help alleviate air pollution in China. Mr. Wang Yilin, chairman of the board of CNPC, believes that operation research has a bright future not only in CNPC, but also in China. He strongly believes that operation research will play a major role in ensuring a sustainable economic growth, fulfilling our responsibility to the society, and promoting development that will benefit all mankind. We'll conclude this presentation with Mr. Wang's video. Thank you very much.
天然气是一种优质、低碳、清洁的能源，特别是中国政府高度重视大气污染的治理和天然气的开发利用。中国是一个天然气利用非常巨大的市场空间。中国石油作为天然气业务的主要生产商和供应商，我们非常支持天然气业务的发展。在天然气业务的发展过程中，也必然会遇到一些运筹学方面的一些关键问题。那么这些问题就需要我们不断地进行管理创新，予以解决。应当说，近几年的工作，我们运用了运筹学的理念，不断调整天然气的业务结构，取得了丰硕的成果。全国人民对中国的天然气利用给予了充分的肯定。我们也非常有信心，把天然气发展的更加的高效，更加的造福于全球人民。
Thank you for your presentation. We'll turn it over.